Good afternoon, everyone. It is lovely to see you all again. So many smiling, bright faces despite the rain that's meant to be coming. I heard some rumbling, so we'll see what the afternoon brings. Today we are going back to linked lists. We've spent a little bit of time already covering structures, covering linked lists and one-dimensional dynamic structures. So these are things that we create via malloc that have like one dimension that we have to conceptualize of. So if you think of a list is a line is one-dimensional, and so it's a dynamic one-dimensional data structure because it's one-dimensional, it's a data structure, and it's dynamic because we're creating elements in it as we go using malloc. This figure that has been part of the title slide for linked lists should now be understandable to you. For each node in our linked list, we have some data that's associated with it. In our C code examples, this was the data T type. And we also have a next pointer that points to the next element in the linked list, as well as keeping track of where the head of the list is. So this was Tarish with his policeman's helmet yesterday, reminding us of where the list began. Where we left off was in creating this pop function. This is our new pop function, which is slightly different to the one yesterday. You'll recall yesterday that the pop function returned a pointer to the start of the list. Now we want to do something a little different. What happens if you actually want to access the first element of the list at the same time as removing it? This seems like a fairly natural thing to do. If we're thinking about our Hamilton tickets example, when the person gets to the front of the line, we want to both remove the person from the front of the line and at the same time get that person's details so that we can actually give them a ticket. This version of the pop function is designed to do exactly that. You'll notice that the return type of this function is data T instead of what previously would have been a pointer to the head of the new head of the list. In order to do this, however, we have to actually modify the head of the list so that the head of the list now points to the new head. So instead of having a single dimensional pointer, we now have a pointer to a pointer. So we pass in, you'll see we now have to call this using a pointer to the start of the list so that we can actually modify the pointer of the start of the list and change the value inside it to point to what is now the new head of the list. Let's do this on the iPad, which will make it clearer. Again, talking about some of this abstractly is a little difficult. So let's say we have 3 items, A, B, and C. Each of these just refers to the data T contained at each of them. If we pass into our pop function, a pointer P, which points to this, and then let's say we now have a new pointer P inside here. Actually, I'm going to relabel this to make it a little clearer. I'm going to call that one head. When we call the pop function, whatever head is pointing to gets copied into P. So now P also points to that. And now what we're going to do is we remove that. In theory, we free it up, and we change our pointer P so that our pointer P now points to that second item there. However, if we don't return P from this pop function, when the pop function ends, P is just a stack variable inside of pop. So P would get destroyed, and our original head value, our original head pointer, would stay the same. So what we can do instead is if we pass a pointer to head, so remember head is located at some address in memory, and inside 71F, and let's say that this is address 1, the address 71F contains the value 1. So let's say instead of passing the value 1 and copying the value 1 over into here, if we pass a pointer to a pointer, and this pointer now contains, instead we pass in 0x71F, which is a pointer to head, we can now modify what's located at 71F, and 71F contained 0, 1. And now we say, 0, 1 is this thing here, but that's incorrect now because we have a new head of the list. What we should do is we should use this pointer inside our pop function, dereference it, which takes us over to here, and assuming that this value is 0, 2, if we change the value at 71f to 0, 2, now when the pop function ends, we clean up its stack frame, and head now points to the new value 0, 2 over here. This allows us to not need to return the new head from the pop function. So before, we were returning the value 0, 2. Now we don't need to return 0, 2 because what we've done instead is passed in a pointer to the head, and by modifying head itself, even though it was part of the original calling function, we can now return a different value from this pop function. And so we can return instead A, and let's say A is the name of the person we wanted to give the ticket to. Returning to our slide, we can see this is exactly what we're doing in the C code. We take in a pointer to the head of the list, which is itself a pointer. And we do roughly the same thing before, just accounting for the fact that now we have a pointer to a pointer. And at the end, instead of returning the address of the new head of the list, we can return stuff, which was the contents of the data at the head of the list. So this is going to be a little tricky to absorb just through what we've gone through. Again, I encourage you to draw out with a pen and paper, step through the individual instructions in this, and it'll make it a lot easier to understand. This gives us a sense of why we might actually be using malloc. This complicated data structure enables us to add people as they arrive rather than just at the beginning. So you could imagine a C program that is, say, connected to the internet. And as people log onto Ticketmaster.com, when someone new logs in, it allocates some more memory for that person in the linked list and adds their name to the list. This is really helpful because potentially we don't know how many people are going to want to line up for the Hamilton tickets ahead of time. And so if we allocate room for only 100 people using, say, an array, then we would have to go through the expensive resizing operation every time that we exceeded the bounds of the array. So when the 101st person came along, we'd have to do a realloc and make the array bigger. And that's obviously not as efficient as our linked list, where we can just add each new person on. And we'll talk a little more about efficiency at the end of this segment on linked lists. We now go back to an audience question. We have our data structure, our linked list. We know how to do certain operations with it. What two functions do we need, or what two operations do we need for our linked list in order to build a queue? What was your name?
Aris.
Aris. I think I remember you from much earlier in the semester.
Yeah.
Yeah, okay. So if we have our group of people coming in and our group of people leaving, and let's assume that for the time being that Albert used to leave from the middle of the queue, but let's say that we're only going to allow people to join at the back and leave from the front. What two operations do we need our linked list to be able to handle?
We need to pop the first.
Yeah, so we need to be able to remove the person at the front to give them a ticket. And what other operation do we need?
And move every person forward.
So do we need to move every person forward in the linked list, or does our linked list know what the new order is automatically?
It knows automatically because it has a pointer point to that.
Yeah, so it's got the pointers, so we don't need to move everyone along. So you recognize that we need to, you've already told us that we need to be able to remove someone from the front of the queue. What about when someone new comes along?
Then
someone new comes along, what do we need to do to our linked list?
And the last pointer point to the
You don't need to explain the operation, just what do we do when a new person comes along? It's a simple question.
just let it join into the queue.
Yeah, and where on the queue do we put them? Do they go at the start if they just show up?
They go at the start.
Do they? If someone lines up, we're all lining up for tickets and someone new comes along, do they go at the start of the line?
Oh, no, just the end of the line.
They go at the end of the line. So remind me again, you've said it already, but what are the two things we need for a functional queue? You've already said them both. So we need it when someone new comes, we
We
when someone new comes,
we add it to the
add them to the back. And when someone old is ready to leave, we
leave
remove them from the
first.
front. So this makes up what we call another abstract data structure. Just like the linked list is an abstraction over either arrays or pointers, it doesn't really matter which you do, you can still do the same operations. Queues are somewhat similar. As long as we have some way of adding people to the front and removing people from the back, we've got a queue. And in computer science terminology, queues are special in that you can't just pick someone out from the middle. Queues refer to specifically this property that you have where you can remove things from the front and add things to the back. And this makes sense because there are a lot of instances where instead of talking about people joining a line, you might be talking about the order of things that have been added to a database, and you want to remove Leah? Anyway, someone is having too much fun taking over mutinying again. So queues do model a whole lot of different aspects of things that we might want in a computer science perspective. And remember that when we refer to a queue, specifically in this context, we're talking about only removing things from the front and adding things to the end. And we can implement a queue in all kinds of ways. Linked lists were one, and arrays were another, but the key thing is to be a queue in computer science, you just need to support these two operations. We have insert at tail, so put something at the very end, and extract from head, take something out from the front. What about a stack? Now remember, the way a stack works is just like a stack of paper. So if you put, say, 3 pieces of paper on, the third piece of paper that you've put on is now the one at the top, and so that should be the only thing that you can remove. So what two operations do we need if we want to create a stack?
I guess you need to pop the stack, and you need to be able to add onto the front of the stack.
Okay, so explain to me what pop does. What does pop do?
So pop removes the first item off of the stack.
That's if we're conceptualizing it of as stack. What if we're thinking about it as a list of items?
Just remove the front of it, I guess.
If we're removing the front, doesn't that make it the same as a queue? The front was the first thing that was added, and if it's a stack, the first thing that was added is at the bottom of the pile.
Oh, sorry, remove the tail. Right.
So we remove the tail, and where do we add new things?
Also at the tail.
So one way is of doing it at the tail, but it doesn't really matter which one we call the head and the tail. They're kind of interchangeable. So the key point for a stack is that you insert and remove from the same side as you put in. So the most recent thing you added is also the only thing that you can remove. Just like pieces of paper, if you have a stack of pieces of paper, assuming that you're not like going in and making the whole thing fall over, or maybe Jenga blocks is a better analogy. If you're putting Jenga blocks on top of each other, you can only reliably remove the last one you put on top of the pile without making the pile fall over. So we can either call this the head or the tail. I've chosen here to call it the head, and for implementation reasons, this often makes sense. Now we're back to some code demos to actually get more of a feeling for how all of this works. Okay, so the first one we have is a program, and I will bring this up in a moment once it's ready, that allows us to insert an item to the end of our linked list. Thus far, we've only seen push, which is add something to the front. We also want to be able to add something to the end in order to give us a queue. No, there we go, on switcher number 2. The first thing you'll note about this program is that I have this weird hash define here that is a bit more of a complex find and replace than we're used to. Oh, one other note before we go on. All the programs from today I haven't had a chance to put on the internet somewhere yet. I'll get that done after lecture so that you can follow along when you rewatch the lecture or do the review. I will also check them for bugs. I wrote many of these programs this morning, so if you spot a bug, let me know. So our hash define here is a little more interesting than usual, because this time I'm hash defining a function. And remember, the way a hash define works is it replaces every instance of the first thing with an instance of the second thing. So I am replacing every time I have calling a function insert at end with arguments x and y, I'm replacing that with insert at index xy and then a function list length y. This is because inserting something at the end of a list is the same as writing a function that inserts it at a particular index where the index is the very end of the list. So if I have a function that allows me to insert at index 1 or index 2 or index 3, if I insert it at the very last index, that's kind of the same thing. So I'm doing this nice hash define just so I don't have to write a special insert at end.
Just let me do this while you do that.
Insert at end.
I just had a question about hash defining the function call. Because you had a call to another function in the hash define, does the compiler read that as a prototype?
So the compiler does not read it as a prototype. What the compiler literally does is it looks for every time this is written, or I should say the preprocessor, because hash defines are run before compilation. It looks for every time this appears and just replaces it with that. However, the preprocessor is also smart in that it doesn't need to be the exact letters x, y. It treats those as function arguments. So every time it sees insert at end followed by some arguments of any type, it replaces it with this exact string, accounting for the fact that x and y are swapped out for the arguments.
So you wouldn't get an error for like having the function named there before prototype?
No, you don't get an error. This is exactly like running copy replace, and then compilation of the program happens. Okay, where were we? We were talking about how to get the length of a linked list. So the basic idea here is fairly simple. This would be another opportunity to go into the audience, but because we're a couple of minutes behind from some of yesterday's discussion, I'm going to power through this. In order to figure out the length of a list, you can either ahead of time store how many items are in it and then add one to your count each time you add a new item. But for the time being, we don't have a structure that represents the list itself. We just have a collection of nodes. So the only way we're going to be able to do this is by going through the list and then counting how many different items we see. And that's essentially what this does. We start at the head, and then while we're not looking at a null pointer, increase the count by 1, and visit the next item. Eventually, if we visit item 1, item 2, item 3, item 4, and say on item 4 points to null, at that point, P will become null because we've just said that P is the next thing along. This loop will fail, we'll exit, and we'll return the value of I. What is the runtime that you need in order to get the length of the list under this particular implementation? Why you gotta wait for me, but he's right. You can say that again into the microphone.
It's big O of n.
It's big O of n because we have to visit every element in the linked list in order to figure out how many there are, because we don't know where the null pointer is going to be until we actually hit it. So this might not be the most efficient thing if we're going to have to get the length of the list or use it over and over again, like I'm using here. So this is probably not the most efficient version of the linked list code you'll find. We will get to a more efficient version in a little bit. Now let's look at the insert at index function. Here is insert at index. Ooh, I'm getting some, yeah, I know what this is. Don't worry, Liam. So this function allows me to insert stuff at a given index, and it works quite similarly. While we're not looking at, if index equals 0, which means we're trying to insert something at the head of the list, that's a fairly easy operation that we've seen before. That's just our push. If index is anything else, starting from the head, which was the thing we passed in. Hopefully we passed in the head. Starting from the head, jump along until you're at the index where you're going to insert the thing, and insert the item by setting its next pointer to what was previously the next pointer of the item you're looking at, and then rebuild the other link. This is going to be a little tricky to, again, conceptualize without an example. So we will move quickly to the iPad, look at how this works. But I'm not going to go through it probably today in enough detail for you to really understand it deeply. This is another one of those examples where you're just going to have to draw it out and get a feel for it. So this time I'm just going to draw series of nodes. And underneath them, I'm going to write what their contents were. Null. And let's say we want to add Q, but we want to add Q between B and C. So in order to add Q between B and C, first we have to navigate to B. So we follow along our links until we get to B, and we say that we want to insert it at index 1. So we have a counter, we start here, our counter is at 0, we go here, our counter's at 1. Now we're at element B. We want to move B's link so that it points to a new node. Going to create that node and put Q in there. Unfortunately, B and Q look a little similar. And then we want Q's link to point to the same thing that B was previously pointing to. So we take this link here, and we keep track of what it was previously pointing to, but we reattach it to that node there. And so in order to do this, we had to keep track of what B was previously pointing to. So that was in our code. That was third time lucky. In our code, that was p.next. And then p.next, new.next equals p.next, and then p.next equals new, completing our operation that we just looked at over there. Now you'll notice one thing in this, we're still looking at that. You'll notice one thing in this version of the code. I'm using string copy to copy stuff in instead of new data equals stuff. And let's see why I'm doing this at the top here. The reason I've had to actually modify our linked list code from before is because I'm setting data t to be name t, and name t is a character array. And remember, with character arrays, you can't set two arrays equal to each other. And so if I have the data member or the data element of one of the nodes in my linked list, I can't say data equals this array, because that'd be trying to set two arrays equal to each other. So this is one trap that you can fall into if you're trying to use strings in the form of fixed size character arrays in your linked list. So one way of doing it that we've seen right now is to switch everything out and use string copy in all the places where we previously were doing assignment. We will see another way of doing it in just a moment. Now let's look at the main block of code, our main function here. We create a new head. Because the head is currently not pointing to anything, we set its next pointer to null just to be safe. And also so our functions work, because our functions rely on seeing a null pointer at next. And then we're going to copy Albert's name into data, because he was first in line, I think, yesterday. No, he wasn't first in line. This time he's first in line. He's got a better memory for it than I am. And then we're going to insert Wida, Nash, Noah, and Maheen to the end. And apologies if I misspelled your names. I didn't collect the spelling from you yesterday. Maheen, how did I do? We're good, okay. And Nash, I'm not sure if you're here. Oh, you're all the way in the back. How do you spell your name? Okay, I got it right. Woo, that was a good guess. Let's give this a run. It shouldn't crash. I know there's an error in the code somewhere, but it's not that one. At the very start, we have inserted Albert, then we've inserted Wider, then Nash, then Noam, Maheen, and we see that it's in the order of in which they arrived. Then I can do my pop, which removes the first person from the queue, because Albert has gotten his ticket, which leaves Wider, Nash, Noam, Maheen. We pop the second one, leaves Nash, Noam, Maheen. Okay, that seems to be working pretty well. What was next in my beautiful list? We had polymorphic string. Okay, now I have changed the type of data T. It still points to name T, but now name T is not an array of a fixed number of characters. It's now a pointer, a character pointer, which remember we can use for strings. What this means, though, is that every time here that I was previously doing string copy, I now instead can use a fixed string directly, because we can set strings, we can set pointers equal to each other. And remember that we have this special way of allocating strings into a different part, neither the stack nor the heap. One of the fixed elements, I think it was wasn't the BSS, it was the, yeah, it was the, no, not the code, I think it's the data segment. I'll have to refresh my memory on this. But if we have strings that are allocated like, initialized like this, then they go into the special part of memory, and it automatically sets up the pointer for us. So now we can set it directly. And if we look at our insert at end function, oh, that's still referring to insert at index. If we look at our insert at index function, we can see that we can assign stuff directly because now we're using pointers. This has the added benefit of allowing us to use a line here, new data equals stuff, without worrying about the type of stuff. This is called polymorphism, because if we changed data T up here to be an int, we'll get some errors now because there are other places where I'm trying to use insert strings. But if I did change that to int and changed all of these to integers, the code would still work if I did that, etc., etc. But we'll reverse that change so we can see this one running as well. It should do pretty much the same thing. There you go, same result. Okay, now we have some bad code, and this one I should add a warning here for when I publish it. Mostly the same as before. Instead of doing insert at end, I'm using push. And there is a problem here. Hey, what's that look? Okay. You're just visiting? Yeah. What was your name?
Amy.
Amy, well, it's a pleasure to meet you. I presume you don't want to answer the question? More than welcome to try, but there you go. Remind me your name again.
Chris.
Chris. Okay, Chris, hold up the microphone a bit. Okay. You feeling all right? What's the question? Yeah, we haven't gotten there yet. So the question is, what is the error in this code? And I'll help you out. Look at it for a second, and then I'll give you a hint. So when we push something to our linked list, what are we doing to the front of the linked list?
Just the push arrow.
Yeah, when I push something to a linked list, remember a push adds something to the front. What have I done to the start of the linked list? Kind of said it earlier in the sentence.
Actually, no, I shouldn't.
Okay, so just kind of think through what I just said. Okay, keep holding the microphone. Don't worry, if we don't get it, we'll move on in a second. But the push operation is designed to add something new to the linked list, right?
Yeah.
Yeah. And so what happens to the start of the linked list if I add something new? Is the start the same as it was before?
Yeah.
If I've added something new, if I have a list, if I have a line with one person in it and another person comes along to the front, is that the same as before or is it different?
Same.
It's different because there are now two people, right? Because I have the person who was there before and now the new person. And so if I'm trying to keep track of who was at the front and I'm looking at, say there's Adam and Eve. If Eve was here before and I say Eve's at the front of the line and now Adam comes and pushes ahead, Adam is now at the front of the line. And so I have to update my thinking because I'm thinking Eve's the front of the line, Eve's the front of the line, Eve's the front of the line. Adam's along here now. Eve's not the front of the line anymore. So what I'd have to do is change what the head is. I'd have to change my thinking of who's at the front of the line to point to Adam. And you'll notice here I've not quite done that. What I've done is I've put a new person in the line, but I haven't actually updated my thinking of where the front of the line is. That's my head variable.
Wait.
So Chris helped us to spot the bug in this code, which is that I'm adding things to the front of the line without updating who is actually at the front of the line. Don't worry about it. We're good. So this is the corrected version of the code, where now each time I add someone to the front of the line, I update my head variable that keeps track of where the front of the line is. So let's see what happens if I try and run the bad version. I'm not actually sure I ran this one this morning. Oop. I accidentally overwrote it. Thankfully, VS Code saves me from errors like this. Yep, I get an error as soon as I try and remove something from the list. And if you want to figure out exactly what was going on, this is an exercise for you, once I publish the code, to take it home and figure out why the assert is failing and what I've actually done to my memory as a result of this. Now let's run the better one. Okay, there we go, working as before. Yeah.
Yeah. So for the head equals.
Let's give you a microphone so that the Zoomies can hear, and so it comes on the recording.
So for the head equals of the four pushes, would that just be head equals the string or?
No. So remember, our push function returns what the new head of the thing is.
Okay.
So once it creates the node and adds it to the front, it returns the address of that node. There was another question.
Yep, so instead, can I design the push function so that you pass in a pointer to head instead? And
Yes, you can. We are about to do that. You're stealing my thunder. Shh. No, it's good that you spotted that. I'm not 100% sure we'll get to it today, but if we don't, we'll get to it tomorrow. But this is only one way to design a linked list. There are slightly better ways that will improve both our efficiency and our ability to handle things without having to worry about writing code like that. So that was our better push pop. We've still got a few more examples of do's and don'ts with linked lists. Our next one is badstring.c. We're going back to our pointers, and this time we are now going to use dynamic allocation. We're going to use malloc for each of these strings. So we'll create a string for Albert, and then we are going to allocate the memory in size data in the data element of the head for his name. So we calculate the length of his name, +1. Remember, the +1 is for the null byte. And then we copy whatever was in there before. So we could have also written this as an array, and that should, yeah, and that would work. So now, even though this is an array, we can still use our character pointer, assuming that we are willing to do a string copy manually, which had some issues with it, but this is just illustrative. So now let's look at our insert n. That's going to take me up to the top. And I'm doing my string copy here again. And every time I do the string copy, I'm going to first allocate memory for that string that I'm putting in. So this is another way of doing a similar thing. However, again, we have a bug. So first, let's look at the rest of the main function, and the bug will become a little clearer. So we're doing our same thing as before. We're adding things, then popping them from the list. And then at the end, remember, it's important to free all the memory that you've allocated. Every time you've done a malloc, there should be a matching free to free up that chunk of memory. Let's take a look at our free list function. Our free list function it iterates through everything that remains in the linked list, even after we've popped some things. And then for each time that we see something, we free it. Now, this is a bit of a trickier question, so it's okay. I think, Yash, you don't want this one? Fox? Nope. Who's up for a trickier question? What was your name again? Evan, I'm sorry. I'll get there. So do you already know where the bug is?
I think so.
Okay, so why don't you give us a try at explaining the bug, otherwise I'll help you find it.
So when you're doing, sorry, can you scroll back up?
Yeah, so I'll go down and you stay up and then, oh, thanks Liam. Okay.
Just the main function. Okay, so here's my thinking. We're only allocating Albert dynamically, but the rest are stored in the data section. So if we try to free those strings, they're not actually dynamic memory, so I'm pretty sure that might end in a seg fault.
Not quite. You're kind of on the right track. Liam, can you scroll down to the insert at index function? Yeah. Okay, so you'll see that we are actually dynamically allocating memory for each of the data regions. My question's probably a little more closely related to how we're freeing things. So Liam, do you want to go down to the free list function at the bottom? Is every malloc matched with a free? So which of the mallocs in my code does this free here refer to?
Hold on. So does it not free like the... Does that list go through every node?
Yep, that goes through all the nodes.
So then it should free... Hold on. Oh no, it only frees the node, but it doesn't actually free the string inside the node.
Very good, okay. Thank you very much, Evan. I'll probably remember you for next time now. So let's explain what Evan meant a little with reference to actually going through the code. That'll make it a little clearer. So Evan thinks that there are places in our code where we have dynamically allocated memory but haven't freed it. Well, let's look at all the places in which we use malloc. So we use malloc on the head to create the node. We use malloc to allocate memory for the string inside the data element of the head. Then every time we insert something, we do another malloc for creating the node. And then we add another malloc for the data that we're putting in the node. So in both instances, we have two mallocs, one that allocates memory for the node and one that allocates memory for the data. Now let's do the same thing for free and see when we free something from the list, do we have two frees, one for the node and one for the data? Well, it doesn't look like it. We've only got one here, where what we're missing is something like free. Because remember, it's every malloc that has to be, not sure how that happened. It's every time conceptually that we've allocated memory, we need to free that chunk of memory somewhere. It doesn't mean that I need to, if I've written malloc 5 times, there will be exactly 5 frees. But for every place that I've allocated memory, you have to keep track in your head when writing your code quite carefully, and you have to match it up so that every place in memory that you've allocated is going to be freed. And because I've allocated a place in memory for each one of the data elements, which is containing my dynamic strings, there also needs to be a matching free. However, my code still has a bug. Let's search for the other place where I'm potentially freeing the memory. Oh, it looks like there's another free here. When I pop something from the front, that's also an instance of freeing. And if I remove the head of the list, but only destroy the node and don't deallocate the memory that's located to, I've done the same thing. I also have a memory leak there. So this is the other instance in which I'm trying to remove a node. And so I'd also need to do old data there. So this is my bad example. Let's give it a run and see if it works. And the answer might surprise you. Maybe.
The other terminal's still open on the side.
Oh, there we are. Thanks, Liam.
Second.
Yeah.
There you go.
Clang. This was called bad string. Works perfectly fine.
Even with back.
Yeah. So the reason that it's working fine is not because we don't have a bug. We do have a bug, and it's potentially a bad bug. There are two reasons really why it's working fine. The first is that we haven't touched any memory that no longer belongs to us. All we've done is abandoned memory. It's still allocated, and we've just forgotten to free it. So if we kept doing this over and over and over, we'd get more and more memory that we have allocated but haven't remembered to remove. So we might eventually, if we keep doing this, we might get a heap overflow and use too much memory in the heap. But also, when a program ends, the operating system has already kept track of all the memory that it has allocated and says, okay, the program is dead, so obviously any memory that the program has previously allocated should also be cleaned up. So the operating system fulfills a really important function here of reclaiming the memory if you've forgotten to do so. That doesn't mean that it's okay not to free things, because you don't want to be like Google Chrome used to be and keep using more and more memory, particularly if your program stays open for a long time. So it's still a bad thing to have these bugs, but it won't necessarily result in an instant error. Now, it used to be in the old days of coding, when I was just a twinkle in my parents' eye before I was actually born, that it was very difficult to detect these bugs, but thankfully, in the many years intervening, we now have a number of tools that one can use to detect these. And while some of this is going to be left for much later in the semester, potentially in the last week, I will post two little lines here that might work on your computer, they might not, that you can use to try and detect these memory leaks. So if you're on a Mac, this first one is going to be one way to do it. There's a program called Leaks, which runs your code and monitors every time you do a malloc to check if there are any places you've done a malloc and where the memory hasn't been freed later. And it does this by intercepting malloc and keeping its own list of everything that you've allocated. So let's give this one a run. It's called Leaks. Nice. And you can see after it runs, if you scroll up, there's the normal output from the code and gives us the process, where you ran it from. But it also shows us that there are leaks. There is a leak of length 6, 5, 4, 4, and 6. These are all the strings inside the data element that we have forgotten to free. And so it even gives us how much memory we've actually leaked in this one. The results from programs like this, like Leaks or like Valgrind, which will run on Linux, or for those of you running Windows, you can install Valgrind within your Windows subsystem for Linux special thing that you've been running. You can install that. These programs are not perfect. They will not always catch every memory leak. They will not always give you accurate results or tell you exactly where they happened, but they can be really, really, really useful for helping you to spot them, particularly when you're in instances if you don't understand your program's behavior. So I would encourage you to give these tools a run. One of the nice things about Valgrind that this Leaks program doesn't do is Valgrind attempts to give you the location in your code at which you've done the memory allocation in the first place. And let's see, we've got one more minute, and I think this is a...
Can you try fsanitize address? It should also...
Yeah, I'm about to do that, Liam.
Sorry.
So this needs a little bit of working to get running on a Mac, but with a few extra flags.
Oh. I always thought that the leaks was always on for ASAN.
Now if let me just check that the Clang is the right one. I'm not sure I have the right version of Clang on this to make it work. Oh, it looks like I do.
Yeah.
And this was called badstring.c. So the reason okay, it's not going to work for me today. I will, if I remember, put up a video of this one working,
Maybe try your usual compile.
I'll try my usual one,
And
and we'll just see. But there is a way of getting this working on Mac. It's just a little convoluted, where you can run something very similar that does give you the location as well. Let's try that. It might work. No. Yeah. So you have to have installed a special new version of Clang for this to work, not the one that comes built in with Mac. And that's where we'll leave it today. Tomorrow we will go into how to calculate the efficiency of all these various programs and how to potentially make our linked list a little more efficient. And then if you're lucky, we will finish off the last segment for me with binary search trees. I hope you all have a wonderful afternoon, and I will catch you tomorrow. Thanks very much.